Well, thank you very much for your kind introduction. Ladies and gentlemen, thanks for being here. Thanks for your interest in our technology, in our project. And I would like to give you some more details about Maglev fascination in general and the Shanghai Maglev Trans-Rapid project. Show you some pictures about the coil winding technology we are applying and give an outlook on the technology in the future. And the first function, features, technology driver. Why did we create Maglev? What was the impetus to create Maglev? Well, first of all, to achieve higher speed. But speed is not everything. But the fascination at the beginning was actually no physical limit of speed. Looking in more details, it's a contactless operation with no noise of rolling wheels. From today's point of view, this is the most interesting feature, and no wear or tear. Maglev can provide high-speed daily operation without actual demand of maintenance work with regard to wear and tear of wheels and rails. I think you know how Maglev works. The basic effect is the energy transmission or propulsion in the track, not in the vehicle, in the track. There is a long stator motor and levitation magnets in the magnet, and the levitation magnets itself provide the magnetic excitation of the linear motor. And in addition, there is a guidance system for the guidance. The performance itself is the actual higher performance in terms of speed, acceleration, and riding time, and also a lower energy demand at given speed, due to perfect aerodynamic considerations. And also very important, more flexible alignments in terms of curve radii, inclination, easier to implement in a given infrastructure. And at the end, a shorter construction time on site. The cost of Maglev is actually competitive with other high-speed rail systems. It earns around 25 to 30 million euro as an overall system price. And Maglev provides very low costs for operation and maintenance. The first item is fully automatic operation, driverless train sets, and very low maintenance cost due to a friction-free and low maintenance condition. And that's what's exclusive of Trans-Rapid, that it's possible to have a very close collocation of the Maglev track with existing expressways, and a nearly noiseless operation in areas of mega cities. We can operate at about 200 kilometers per hour at very, very low level of noise emission. A famous colleague of mine in Japan, Professor Masada, talked about the first 100 years of Maglev. That may be surprising, but the first patent on Maglev came out in 1912 in the US. And it was a French expert who gave his first invention of a Maglev system. And then the later patent that was the basis for Trans-Rapid, it's Hermann Kemper, who created this first idea of Maglev in the 30s, but no chance to realize due to lack of power electronics and signal electronics. And it was another visionist, it's Ludwig Bölkow, the head of former MBB, who picked up this idea and created a first test track in the 70s. And behind this first project was the political approach saying, do not put all research efforts into road, also promote rail ground transportation to achieve a higher performance. That was the initiative to start. And then another 3 big milestones: a first passenger transport in Hamburg. There was an international transport fair in 1979. That was the first time public could use maglev. That was in Hamburg. And well, 2 more records in Japan. A different system was at the same time further developed. That's in Yamanashi in Japan, and they achieved the ground speed record of more than or nearly 600 kilometers per hour. I will later address this test track at the end of my presentation. And of course, that's the story of the presentation, the first commercial line in Shanghai, where we have public transport since 2004. Maglev fascination was a technology driver throughout the entire period. Some examples: there were some essential key technologies which were initiated by the Maglev program. One big example is large power inverters in the area 2 to 5 megavolt amps. In the time of the early 70s, nobody was interested in such kind of inverters. Only these crazy Maglev guys were the one demanding a high power inverter. Later, this became the basis of all AC drives in locomotives and large industrial drives, and somewhat later in small industrial drives. And also linear motors in industrial series productions. The roots, the basis started in this period. Inverters running at very high switching frequency, also a promotion from demand of Maglev in the 70s. Inverters with electronic safeguarding, also an important feature. Only Maglev people demanded safety issues in power electronics. Many people said, well, it's absolutely impossible to have safety features inserted in an electronic device. Today, it's very clear that it works. At that time, it was a big demand, a technology driver. Then safety location, up to 500 kilometers per hour. And then the story of this conference, magnet poles, epoxy casted under vacuum conditions. This technology also was created in this period under the demand of Maglev. Large, lightweight carriages, automatic control, driverless operation, and high-precision guideway beams. Guideway beams of 25-meter length with a tolerance of 1 millimeter. It was a big challenge for construction industry. Normally they thought in tolerances of some centimeters. Now the crazy Maglev guys demanded a tolerance of millimeter. And that provided also a big revolution in the concrete element industry. So why do I tell that? I tell that to tell you such technology programs create a lot of innovations, whether the basic issue is successful or not. There are basic inventions and technologies following up. Now the Shanghai Project, here you see some pictures. The key figures, it's only 30 kilometers to connect the airports to the end of downtown area. We have a trip time of 8 minutes, headway of 10 minutes, and the top speed is 430 kilometers, which is still run today. Not all the time because of some peak power issues, but it's a normal speed. And punctuality is 99.9. This is an excellent figure, owned by 2 issues. There's a separate track, and Maglev system is based on redundant structure. Failure tolerant, any component may fail. The system continues operation, and that provides a perfect availability and punctuality throughout the time. That was also record. Contract signature in January 2001, and the VIP run with the Chinese Prime Minister and the German Bundeskanzler less than 2 years later. And then 1 more year later, the acceptance. So that means actually 3 years behind contract signature and acceptance and start of public operation. Really a record and an excellent performance of both parties, of the Chinese side of SMTDC, under the head of famous Commander Wu Qianming, and the German consortium of Siemens and ThyssenKrupp. I'm sorry to say the movie doesn't work. I have to skip. Some more figures. There are 3 vehicles running out of our supply, and 1 more vehicle has been manufactured by our Chinese partner on the license base, so that there are 4 vehicles in total running, and 19 cars in total. Passengers per year is about 4 to 5 million, and up to now about 35, approaching 40 million passengers have used Maglev in Shanghai, and all these vehicles in total have passed 12 million of kilometers. And my colleagues 2 weeks ago had executed the 10 years inspection according to our maintenance manual, and they stated, well, there is actually no finding of defects or whatsoever. That confirms the basic strategy of these vehicles. And this is a very consequent, lightweight structure, and it's, I feel, a very important feature. One more issue, operation and maintenance has been performed by the Chinese colleagues just from the beginning. Just after the acceptance in 2004, the Chinese staff is doing operation and maintenance. And that means that Maglev is not something for very special long-term specialists. It can be applied, it can be operated, can be maintained by local staff. And the basic issue behind it is a perfect diagnostic system indicating failures in the electronics, in any functions, and telling the maintenance people what to do at the end of the day when the vehicles are returning back to the center. Some pictures of the component technologies, just with regard to, I have to wait, computer is somewhat slow. Here we are. What is inside a Maglev vehicle? There is, of course, a vehicle body. I told it's a very lightweight construction with an aluminum sandwich construction, laser welded, and of course a front desk and a computer diagnostic control. Then we have power networks with batteries, electronic units, and last but not least magnet poles and sensors, and both the sensors and the magnet poles are epoxy casted in vacuum conditions, and in particular the magnet poles are exposed to the natural environmental conditions. Summertime, wintertime, heavy rain, even snow, and that proves that's kind of technology to have such components exposed even to very unfavorable climate conditions. And design principles, again, the basis is autonomous units. So that means the units perform all their functions by itself, and there is a low unit power. The maximum power of any device is 400 volts and about 100 amps maximum. So there is a low power range and a low power of the module. And the small unit size These units are line replaceable. At the end of the day, if there is any defect, you pick out a unit and insert a new unit, and the system is restored again. And at the end, there are only standard materials. All materials you can buy here on the exhibition, you can configure and set up the Maglev vehicle. So there are no very special materials in it. New is the configuration. What coil windings do exist, for which kind of functions? Propulsion, levitation, the guidance, and the safety braking. The propulsion, the long stator motor winding is inserted in the guideway, and it is a cable of 20 kV with aluminum wire. That's in the guideway, and the levitation magnets at the same time create the excitation for the linear motor in the guideway. That's an aluminum band wire in epoxy, and also same technology for the guidance magnets and for the safety braking. Safety braking as an eddy current brake with multiple independent units providing the safety by independent redundant configuration. Here you see a magnet module on the bottom side, the levitation magnets, which at the same time fulfill the function of magnetic excitation and levitation, and in the gap in between, the gap sensors, measuring the gap between the vehicle and the guideway and providing the closed loop control for the magnetic current. And same situation for the guidance. And some details of manufacturing. On the right side, the brake magnet pole. On the bottom, the guidance magnet pole. The guidance magnet pole has a length of 0.8 meter. It's a particular geometry. And the entire vehicle and its levitation and guidance is composed by such small modules. Here you see a levitation magnet pole before epoxy casting with the glass fiber armoring. Here, just before casting, the brake magnet poles. And two more functions in the vehicle: power generation on board. Power generation is also provided contactless. And there are two techniques: a linear power generation by a generator in the levitation magnets, and an inductive power transmission, which is contactless to supply the vehicles at 0 speed or at very low speed. The first one is a generator. The second one is a contactless transformer. And some pictures, again, the levitation magnet pole, and you see the coils of the linear generator inserted in the pole core. Next, the inductive power supply. These are length of roughly 1 meter. That's the pickup antenna in the vehicle, operating at a frequency of about 20 kilohertz. This is composed by ferrites and a coil, and that is again in an integrated cladding element. So this cladding element is a plastic part, a multifunctional plastic part, including the power pickup for contactless power supply. This technology has been experienced in our test track, and it is, it's a kind of large prototype for inductive power supply, which is now under discussion for electromobility. And these are the guys who are manufacturing the parts. This is my colleague Joachim Cwieme, who is in the auditory and also exhibitor on this congress. They have the knowledge and the expertise to manufacture the magnet poles I have presented to you. Well, last issue, Transrapid opportunities, look into the future. What about the technology? You all know it's not under current application in Germany nor in Europe, and I do not expect that that will occur in the next years or in the next 10 years. Nevertheless, it's my opinion that Maglev is an option for the future, and there is, I told you at the beginning, the Maglev guys have promoted technology, created many issues that have been absolutely new for electrical machinery, for control, for lightweight materials, for construction industry. Now it's different. Now, from my point of view as a Maglev technician, I say, I observing what others do. And there is a big progress in electromobility, and that provides for Transrapid small size, low cost, low weight electronic units, battery systems, and a significant potential to reduce the cost in the future. Just to illustrate, I'm sorry, as in the presentation, I hope you can see that there is one levitation frame. There are 16 levitation frames in each Maglev vehicle, and nearly the same components as we use it in a Maglev vehicle are being used in an electric car. There are in the car actuators, drive and steering motors, and these actuators in the Maglev vehicle are magnet poles for levitation and guidance. There are battery units in both. There are electronic power components in both, and the size, the volume, the rated power is actually the same. And there are lightweight frames in both. So I expect that the progress in electrical cars, in e-mobility, will provide a technology platform in the future to have a significantly low-cost Maglev vehicle in the future as an option. And that's why I would like to enter into the next 100 years of transportation, saying, well, Maglev is a valuable option. And at the end of my presentation, I would take you to Japan, and actually there, the next 100 years of Maglev have just begun. This is a picture, this is a picture which is a few days old, in the first days of June. This is a new Maglev vehicle created by Japan Railroad. And the Japanese side is now extending its test line, and this test line is appointed to become a first commercial line to connect Tokyo and Nagoya until 2025-30. These are the official figures. That means the Japanese side is continuing its Maglev program, and it's supported by the Japanese railway company. This is a very important feature because they really know one day we have to provide a substitute for the conventional steel wheel on steel rail technology. So far, my outlook into the next 100 years of Maglev, and I thank you very much for your kind attention.